Welcome to Inside xtUML, a learning series. In Episode 3, we will investigate the early steps of creating an xtUML model. Before I begin, I would like to thank the xtUML community for organizing this series and for providing the opportunity to share with you some of my knowledge of xtUML. If you are unfamiliar with xtUML.org, I encourage you to visit the site. This is a community of like-minded members that are actively working with xtUML and are willing to share their experience. As a community member, I benefit from the experience of others and the ongoing development of tools that the xtUML.org community is involved with. As part of the community's effort to broaden the awareness of xtUML, this series, called Inside xtUML, a learning series, was started. These seminars are prepared and presented by community members to share their knowledge and experience with others. I want to remind everybody that these events are recorded and can be viewed by visiting the xtUML channel on YouTube. In Episode 2, the xtUML process was introduced. For those that missed that episode, I've included a brief review in today's presentation. Following that, I will dig deeper into the first step of the process, the analysis step. As we progress through the discussion, I will touch on requirements, provide steps to assist with identifying system domains, and then review the role of sequence, use case, and activity diagrams in this analysis. These activities come together with the completion of a structural description of the system that is expressed in terms of xtUML component diagrams and interface definitions. Throughout today's discussion, I will use the example of a running watch as a case study to illustrate the ideas presented. In Episode 2, the xtUML process was introduced. Beginning with requirements, the first step in the process is analysis, and this step is typically performed by systems engineers. Here, requirements are collected into related groups and a structural specification is produced. These specifications become the starting point for the second step, component design. Components and their behavior are expressed in terms of data members, lifelines containing the control and processing evolution of each data element, and their relationship to other domain members. These component models are executable, so in Step 3, test engineers connect system components to test components and then execute the combined system. The captured results for each test provide the artifacts needed to document validation and verification testing. The final step is implementation, and this work is performed by integration engineers. During this step, the xtUML model is translated from the platform-independent diagrams into a platform-specific representation. In this form, the realized component can then be integrated with other components to form the final realized product. Ideally, a project requires only one pass through this process to get from requirements to implementation. However, my experience has been quite different, and that new requirements or new details uncovered during design will lead to iterations. These surprises are a common aspect of today's systems design experience, and the xtUML approach accommodates them very well. Now, let's look at how the xtUML process accommodates these iterations. In the analysis step, system engineers are organizing requirements in an effort to identify the structure of the system and to document the communication between the domains of the system. This is work that progresses until new requirements no longer lead to modifications of either the structure or the communications interfaces. It is at this point that Step 2 is able to proceed. In my experience, This transition occurs well before all the requirements have been fully analyzed. So even though step 2 has begun, I often see the work of analysis continuing in parallel. The design step is about enhancing the structure produced in step 1 by modeling the behavior inside each domain. Since domains are intended to be autonomous, they are ideal candidates for parallel development or continuous design practices. In each of these independent paths, there is the opportunity to stagger the addition of new behaviors and to flow into the third step, execution, models that are incrementally matured. Also, I often find that as the detail inside a domain model increases, it leads to opportunities where further analysis should be performed. And in the xtUML process, this additional analysis can be performed without delaying the efforts on unaffected components. Even though xtUML models are constructed from diagrams and actions, these models are executable. In step 3, we exploit this characteristic to validate the current interpretation of the requirements provided by analysis and remove many of the bugs that might have crept in during design. In this step, it may be necessary to create specialized test components, and xtUML is sufficient to model these components as well. Once test engineering has completed running their tests and produced the reports they need to demonstrate that a component satisfies the requirements, then step 4 is ready to begin. As with the design step, if bugs are identified in testing, then sending the component back to an earlier step is naturally accommodated by the process. The fourth and final step of the xtUML process is the translation of platform-independent models into a platform-specific implementation. This translation is performed by a model compiler that is constructed to be aware of the attributes of the target platform. The translation produces the implementation artifacts, everything that is needed to integrate and assemble the final product. As part of this activity, system-level testing should be performed, and co-simulating implementations in the same system context is a strong final check. As I progress through today's discussion on analysis, I would like to use the example of a runner's watch to demonstrate some of the concepts discussed. If you're not familiar with these devices, this is a watch that runners use to monitor their fitness while out training. It tracks their location, often using the GPS navigation satellites, monitors their pulse rate, and periodically stores this data until it can be downloaded onto a computer for further analysis. Now, the original requirements for our watch likely started with marketing, and they were presented to engineers as a natural language description. Unfortunately, written specifications are among the poorest ways to share detailed information. Often the requirement descriptions included in these documents are incomplete and must be supplemented by details from standards documents, usage studies, and product history. Beyond the challenge of achieving completeness is the issues surrounding interpretation. Anyone working in this area knows the frustration of creating a concise and precise expression of the requirement, only to learn that designers have chosen a different interpretation. It is at that moment that an architectural bug is born. So the goal of analysis is to distill the requirements into an alternate form, in this case a set of diagrams and procedural statements that describe the structure and actions of the system in a consistent way and with improved comprehension. This set of diagrams and statements that form the analysis model includes a structural description contained in component diagrams and interface definitions, and the behavioral description, which are typically presented through use case, sequence, communication, and activity diagrams. Within the diagrams of the behavioral description, there is redundant detail. As a result, some projects will emphasize the use of use case diagrams, while other projects prefer sequence diagrams to contain the majority of the detail. Neither approach is wrong, but projects should choose one or the other, and projects should avoid choosing to use all the diagrams, since there is the potential for redundant details to be captured inconsistently. I've mentioned that the goal of analysis is to identify structure, and that this structure is described in terms of domains or components. These two terms are interchangeable, though the term domain is popular in the analysis community, and the term component is more common in the UML or xtUML community. So what is a domain? A domain is an autonomous collection of functionality that are mutually dependent and are loosely dependent on other domains. This functionality can act to provide services to other domains or to respond to requests. However, the nature of these exchanges are through very limited and tightly defined bundles of interface messages. For a starting point, it's been my experience that analysis will either start from a blank page or use experience to propose an initial collection of domains. If you pick the blank page approach, then the next step is to sift through requirements to identify request sources that are external to the product. Although these sources have all the characteristics of a domain, they are given the special name of actors. In the case of our runner's watch, the primary actor is the runner, which creates motion, button presses, and paces for the heartbeat sensor. A second source of actors are the related services that respond to requests. And for the watch, that might be something like a computer that accepts data after a training session, or a pulse sensor with adjustable gain. From this starting point, more requirements are investigated, and relationships such as relative location, type of information, services required, or services provided are all items that can influence which domain satisfies a particular requirement. For our runner's watch, each of these diagrams provides potential clues for decisions surrounding domains. The most obvious is the spatial separation between the location satellites and the runner with their watch. This wireless link is a candidate for an interface between two domains, the satellites and the sensors on the watch. So an early decision might be to pick a structure that includes a sensor domain, a storage domain, and a user interface domain. Yet if we next look at the location route charts and pulse rate graphs, we find support for a storage domain and a user interface domain, but there are inconsistencies as well. The nature of the data is very different, and the relationships between pieces of data is largely between items of the same type, rather than between items of different types. Consequently, this information would point to a heart rate monitor domain, a location or tracking domain, and a separate user interface domain, rather than the initial domain decisions. More information is required, and the use case diagram is a popular means to identify these new details. A use case diagram takes a look at the system from the outside and describes how the system performs in response to external stimulus. Since these diagrams are formed from the perspective of an outsider looking in, they are often start with actors and then a series of interactions that are expressed using a set of candidate domains and a collection of requests between domains. Early in the analysis, it is common to construct mostly use case diagrams that contain only one or possibly two domains, which are expressed at a very high level of abstraction. Often these diagrams are at a level of describing goals of the system. In the example, the domain is identified as perform exercise routine, which is a goal, and it includes the request record info which is denoted by the second bubble. As the analysis progresses, the use case diagrams mature to represent a lower level of abstraction. Often the goal-oriented domains are replaced by new domains that are service-oriented, and the interactions become a cascade of service requests. It is important to remember that these new domains should not be described at the level of individual actions. For our runner's watch, the record info domain has been refined to an actor which initiates a service request to store information, and the system response in this usage is described as including requests to retrieve heart rate, location, and time details. One of the challenges of use case diagrams is the difficulty in expressing the order or sequencing of these interactions. To support the modeling of these details during our analysis, the sequence diagram is a better choice. Here the order of interactions is expressed using lifelines attached to actors and domains. When interpreting these diagrams, time advances down the lifeline, but not at a uniform rate. So between two interactions on a lifeline, the best that can be said is that some amount of time has passed between the arrival of the first interaction and the second. These diagrams also provide insight into the concurrency that exists within the system, and where interactions could be sensitive to synchronization. Sequence diagrams are also a rich source of information for the testing phase. The combination of preconditions and a sequence diagram define a test scenario and can be leveraged later on, particularly when the results from an executed test are captured as a sequence diagram. Then there is the opportunity to compare the observed sequence against the expected diagram identified during analysis. Using these comparisons, there is the opportunity to quickly identify and isolate architectural or design bugs. Use case and sequence diagrams are good at describing interactions, but are less effective in presenting processing details associated with a request. To show these details, an activity diagram is used, and while it can be used to show low-level details, it is best during analysis to develop diagrams that show large processing flows. These diagrams are also helpful in documenting a domain that contains a combination or collection of use cases. Having investigated the requirements and constructed a variety of use case, sequence, and activity diagrams, it's now time to construct the component diagram that describes the structure of the system. Each component is intended to encompass a domain or a collection of several coupled domains. From the use case diagrams, we can identify candidate components from the actors and domains included on these diagrams. It is important to remember that components are similar to black boxes that encompass the domains of our analysis. Their implementation is invisible to the outside, and they must interact with other components exclusively through a well-defined set of interfaces at the boundary. As a result, although use case diagrams can be refined to a very high level of detail, when considering component candidates, these low-level diagrams should be discounted and priority given to diagrams documenting higher-level goals and service-oriented use cases, which I highlighted earlier in the talk. For the analysis of the runner's watch, a structural diagram consisting of a location component, a user interface component, a heart rate monitor, and a tracking component is one possible solution. With this structure, each component is autonomous with a consistent collection of services. Also, the message exchange between components is concentrated to a small number of ports with simple interface definitions. Between components, messages are passed, and here sequence diagrams are valuable to identify message clusters that should be combined into an interface definition. With these details, we are now ready to complete our analysis model by documenting the system interfaces. Interfaces are the formal communications mechanism for components. These are bundles of synchronous and asynchronous transactions that go between the domains of the system. Since components are intended to be autonomous service providers and requesters, the contents of the interface definition are largely request and response messages. To define an interface member involves assigning a descriptive name and listing the information details needed by the service provider. For synchronous messages, a list of the expected response details is also required. Each of these interface definitions are then listed on an interface package and attached to the interface portion of the analysis model. For our runner's watch, the adopted component structure leads to a small number of ports and very compact interface definitions. The definitions are organized into services and request messages, and descriptive names have been created. These names go a long way to raising the readability and improving the comprehension of the analysis model. With the completion of the component diagram and the associated interface definitions, Step 1 of the xtUML process is completed, and the design step can now begin. In this step, we have analyzed the requirements and, using the diagrams of xtUML, produced a consistent description of the structure and communication patterns of the system, while clarifying the behavior that will be designed into this structure during Step 2. If, during the design step, details are uncovered that indicate further analysis is required, the xtUML process is structured to accommodate these surprises, and both analysis and design can proceed concurrently. It is challenging to fully explore a topic like systems analysis in just 30 minutes. If you are interested in learning more about the ideas presented here, I encourage you to consider these two books. They offer a good balance of instructional material for those new to xtUML and of reference material for the expert. Thank you for joining me. Goodbye.